Ready.
All right. Welcome to Code Concepts with Steve Regoli. This is your host, Meg Foley. I know that we've had some technological issues today. We're working very hard to try to get everything resolved for you. If you're watching this in replay, you won't have any idea what I'm talking about, and that's totally okay. I'm here with Steve Regoli, who is our Senior Architect Administrator with the Board of Building Standards. He has quite literally helped to write all of the codes that are enforced in Ohio right now. So Steve is an architect. He is well versed in the code. He is the preeminent expert in code administration with the for the Board of Building Standards. If you find your question and answer, you'll be able to chat or ask questions there. This is a live event, which means you are not going to be able to speak, and we will not be able to see you or even who is attending the meeting. We will simply say that I will be monitoring the chat. I'll bring any questions forward to Steve for his erudite answers. So now, without further ado, Steve Regoli.
Thanks, Meg. Appreciate it. What we're going to do today, this class may not be familiar to you. You may have attended before, but we tried to add a few new things to it. But this is a kind of a set the code book down, lean back, and just kind of think through some of this information, because many people don't understand what's behind the codes. How do we get some of this stuff? This isn't going to tie to specific code sections, but it's basic processes and procedures over the history of the development of the codes that stand behind those provisions that you read in black and white. So we've called it Code Basics because it talks about some of the basic concepts behind what we use every day. So remember, if you want to ask a question, there's a chat function, and you can send that question. Meg will get it, and if she can't answer it, we'll talk about it. So go ahead, Meg, and let's start the presentation.
Your presentation is now live.
Okay. As I said, this is a background concept course that will give you a big picture of what's behind these code provisions. So if you have ever wanted these things get developed, some of it is that there's an anecdotal history, some of it is based in research and science, and that's what we're going to talk about today. Well, I always like to start when we talk about the codes about the issues that, unlike other standards, when the building code fails, it has some serious consequences. And over the course of history, there have been a lot of those things that have driven some of the provisions. I always start with something that most of you are familiar with, in that club fire that happened in Rhode Island. And what I'd like to do, this was back in 2003, February, dead of winter. I'd like to run this. Hopefully you'll be able to hear, and then we'll go from there.
Steve, there is no audio in Teams live meetings.
There isn't?
No.
Okay, sorry about that. Well, then what will happen when this happened last time? This was the fire that happened in Rhode Island. It's not necessary that we hear the audio, but I would like the students to see some of the video. Okay?
That's fine.
Now, what happened in this fire was that there was some stage material, sound deadening materials that were along this. You can see it says points of ignition. There were some gerbs or some small fireworks that they used as part of their production. And let me just go back, I want to show you the the interior scenes. Let's see if I can move up. This is during the fire. You can see the band's playing, the fireworks start, smoke starts being generated, and then you can see as the cameraman is backing away, some people are saying head to the door. Other people thought this was part of the show, but now we're seeing fire spread over that non-fireproof sound deadening material, and people are now trying to push to get out. Now, if we move forward a little bit in time, you'll see from the exterior the consequences of failures in properly applying building code requirements. Now, this building, and I'll give you a time frame here in a few minutes, was fully engaged very quickly. There was no way for anyone to leave that building after about a minute. You can see the building is beautiful. Now, the fire started near the stage at the right side of the screen. It was a dance floor, an open room with a lot of windows, a main bar, a kitchen, and some offices. You can see there were four exits really. The front door, a door from the bar, a door from the kitchen, and one over at the side of the platform. Now, if you can imagine, within 90 seconds from the initiation, this is a simulation of temperatures 5 feet above the door. You can see that this entire area had reached nearly 1,000 degrees plus. It spread very quickly, and unfortunately, where most of the people died was right around the front door. There are 31 in this bottleneck. 18 were trying to get as far away as they could from the fire. 9 died in the vestibule. You'll see another 9. They were looking for an exit. There were no exits in the rear of the building. The kitchen exit and the bar exit were kind of totally missed. Now, these types of problems are why we're trying to understand how to effectively enforce the code and what's behind it. Most of the code changes that we have, or a lot of the code changes that the legislatures, the public demands, are from either excessive enforcement, and that's when the board will get a complaint, inadequate enforcement, when there's usually a loss, or a disaster, hurricanes, tornadoes, floods, and those three things have historically driven what is behind the provisions in the code. In this case, there was inadequate enforcement at this club. Those materials had been installed without approval. Fire service had done their investigations, and I think, let me just go back, I wanted to point out that, I think I had, yes, there were 100 killed, 230 injured, 132 escaped in 5.5 minutes. The polyurethane foam produced dark smoke, carbon monoxide, and hydrogen cyanide gas. In Minneapolis, most people don't realize, around that same time, there was also a nightclub fire where the gerbs ignited some material, but we don't hear about it because everyone escaped, because they had actually properly prepared the crowd. They did what the fire code required. They had a pre-event announcements of where the egress, the exits were. They had a staff that was trained to assist in the case of an emergency, and all the people there in that Minneapolis nightclub fire survived. Now, the fire code has provisions for gerbs, these indoor fireworks. It had a requirement for pre-event announcements. It had a requirement for staff training, and unfortunately, because none of that was done, the tour group was fined $1 million. The owners $800,000. The city and state settled for $10 million. The packaging foam manufacturer settled for $25 million. The TV station that sponsored this settled for $30 million. JBL Speakers, the manufacturer of the sound system, was sued, but they settled for $800,000. Anheuser-Busch, who sponsored this tour, settled for $5 million. Home Depot, who provided the foam, settled for $5 million. The radio station, that was also a sponsor, settled for $22 million. The American foam seller, $6.3 million. None of that will ever compensate anyone for the loss of lives and the injuries caused. So what we want to talk about is these things that have driven code changes and what's behind those provisions and how those things were, how they impacted the codes. Generally, we respond to these unacceptable losses after an event. And I've gone back to 1906 and looked at some of those events that have impacted the building code. Triangle Waste and Fire had some impact in Egress, Collinwood Fire, and a lot of the school fires back in 1908 and around that time. Egress, Protect and Place, fire drills, the Coconut Grove Fire in Boston, some of the materials that were used in the building, the Beverly Hills, Kentucky restaurant fire in 1977. Some of you may remember that. The MGM Grand Hotel fire had to do with fire stopping at the perimeter curtain wall. Kansas City walkway collapse had to really brought Chapter 17 into the building code. The 17 that we have today was because there needed to be special inspections for structural components because the provisions were in the standards, but no one looked at the provisions for change orders, structural requirements, and detailing. And as a result of that, there were provisions put in place for structural provisions requiring special inspections. The earthquakes, floods, hurricanes, Scotttown, the Ohio Consumer Fireworks store back in '96 that killed 8 people, brought in some specific Ohio sections in Chapter 4. And obviously the World Trade Center had some impacts for tall buildings on egress, fireproofing, and a lot of other components that we find in the building. So after these unacceptable losses, people say these shouldn't happen. How did it happen? And after research and usually legislation, sometimes there are impacts in the code. Now, there are some tragedies that are not tied to the code. You'll require the New York Social Club fire that happened in 1990. That was an arson fire. 87 people died, but there was a single point of egress, and that building had not had permission to open. North Carolina, there was a chicken processing plant in 1991 where 25 died and 55 were injured. Those were locked egress doors. So there was a security issue, and the owner decided the best way to deal with the security issue was lock the egress doors. So those things that happen are tragedies, but they're not tied to the code. When tragedies are tied with the code responds. We want to look at some of those provisions. Now, in the code, in our provision of law in 3781.11, the legislature said that the board's rules had to do these 3 things. So what's behind Ohio's code really are established by law. And it's clear that we must develop a code with performance objectives consistent with how materials and products are used. Permitting materials and methods, new materials and new methods that might reduce the cost of construction, but maintain acceptable risk thresholds. That's another principle that's behind our code. So when the board adopts new rules, we're always looking at the means and methods and its cost impact. As long as it reduces cost while maintaining or improving safety and sanitation, the board will adopt those new provisions. And then encouraging standardization in methods and materials. Standardization is a great way to drive costs down as long as you don't prefer one material over another. And that's what the legislature said as well. Your rules, Board of Building Standards, should encourage standardization of construction, but they should not prefer one material over another or one class of material over another. And oftentimes the codes are approached by people as a barrier to entry, as a way of securing a unique, favorable position for their materials. And oftentimes in the code hearings, those are discovered and defeated when code change petitions and applications are submitted. And that also happens at the state level. So at the state level, this is what's primarily behind the codes. There are primary considerations at the model code level for life safety, health, ventilation, plumbing, etc. We're going to provide for a healthy environment. We're going to make sure we keep those in the building safe and those around an event safe. We're going to protect property, whether it's critical facilities protection like police stations, power plants, hospitals. We're going to try to reduce the replacement costs for communities, things such as schools and public buildings, that if we protect them using risk management tools, will actually prevent the public from having to rebuild things. Quality of life, energy, accessibility, renewable resources, sustainability, green. While those are not life safety provisions, they do impact welfare. They're more policy issues. So those 4 factors are primary considerations for the model codes when those model codes are being developed. Now, the code types that are being developed generally fall into these categories. There are 3 categories: the land use and environmental type codes. That's the zoning, architectural review, environmental review, that local communities use to establish the baseline for their community, how it should look, where they want things located. Second type of codes, once those land use environmental decisions are made and an owner says, now I know where I can build something, the building design and construction codes, building mechanical, electrical, plumbing, fuel gas, etc., those will say, if you're going to build it, this is how you can do it in a safe and sanitary manner. And the last are the community safety codes. Once a building is located, once it's built, the fire prevention and safety and property maintenance codes make sure that it's maintained that way. And licensing agents control who does work in alterations, additions, and repairs in those buildings. So this set of codes, this family of codes, helps establish a safe, sanitary built environment with those considerations behind them. Now, obviously, if a code doesn't stay current and becomes obsolete, it's no benefit. And we have, since 1979, been part of a national code, model code system that is continuously being updated, whether it's because of new statistics, new methods and materials, an understanding of cost impacts, or certain materials aren't available any longer, or new resources become available. The fact that there's a whole consensus standard industry that develops table leveling standards that explain how something can be manufactured, built, and installed, and then testing labs and certifying agencies to make sure that those standards are complied with in the manufacturing of materials that get used. So this national process is fairly complex. It's provided us with one of the best codes. The model code process has provided us with a set of model codes that are probably some of the best in the world. This process involves a lot of different types of materials, people, labs, universities, design professionals, contractors, owners, code enforcement people. And most don't understand that there is data, statistics, research behind many of the provisions that we take for granted in the codes. And we're going to talk about a few of those so that we can get a feel for how these these understandings and concepts have been developed. We're going to look at several statistics and some research. Some of it's old, some of it's new, but you're going to find some interesting facts that you can see reflected in fundamental provisions in the building code, whether it's an egress, travel distances, fire ratings, all of those things we use to manage risk. So let's look at a few of those. I think you'll find them interesting. First off, when we talk about the building code, we're dealing a lot with fire because buildings are generally made either of or contain things that are flammable, and fire is one of the risks we have to deal with. So when we're talking about responding to fires, we have to understand some things about how people respond. And this is a part of a study of delay times. And this is a list of, an example, a list of events, some of them actual, some of them drills, but you'll see the very first one there is the MGM Grand Fire. You can see that over on the right side. Whoops, let me get back there. This MGM Grand Fire indicates there was no alarm notification, and they grouped data from questionnaires. So somebody actually interviewed the people that were involved in the MGM Grand Fire, and you'll notice here there were about 536 people interviewed, and this is a delay time in minutes for them responding to that event, that fire. You'll notice that the median was 60 minutes. So on average, the people in that building took about an hour to realize something was going on and get out. It was a very tall building. The fire started in the kitchen area on the ground floor and proceeded to burn up the building along the exterior glass line. Because the fire stopping wasn't done properly, it kept moving floor to floor to floor. You can see that the maximum was 290 minutes, and the first quartile, the smallest group, was 3.3 minutes. But on average, it took 60 minutes. Now, as you move down through these, here's the World Trade Center. This was the first World Trade Center, not the 9/11. And you'll see there was an explosion in a garage. And here the median time was 5 minutes in the building closer to the explosion, 10 minutes average on the building farther away from the blast. And then here at the bottom is the high-rise building, unannounced drills. And you can see in normal circumstances, when the drill happens, that the response time is very good, minutes, 1 minute. So if all the systems are working properly and all of the occupants are familiar, you'll see that the egress times are very, very good. This is the time for the first person to get to one of the 4 stairs. This kind of research happens all the time on all fires, on a lot of the fires, because we need to understand how people responded, how the alarms helped, what type of event it was, and that understanding helps us determine, for instance, in the MGM Grand Fire, that there were some provisions needed to be added to the building code. Let's look at the next set of statistics. What about how fast people can move? This is some research on travel speeds, and you'll notice they list several here on the left. You'll see airport transportation terminals. Most people move at about 265 feet per minute. That's pretty quickly. The average under normal conditions is 60 meters per minute. 60 meters per minute. And these descriptions show what happens if you have crutches, cane, a wheelchair, assisted or unassisted wheelchair, so that we can understand how people move, and you can see the mean here, their travel speeds. And in this travel speed, we can understand when we have homogeneous groups, it's different. Everybody is moving at approximately the same rate. But when they're not homogeneous, we have people that might be on wheelchair assisted. That's why in airports you'll see a lot of assisted wheelchairs, because the mean is more than the average under normal situations. You'll see their 1 minute per second is normal. Well, they're faster than that. And you'll see that people on crutches or canes move much slower. Knowing this information helps us understand how people move, the speeds they move in an emergency. Now, when we talk about how this applies to buildings, we kind of look at a description of evacuation time. And most people think evacuation time is just how long it takes me to get from my office to the exterior. But in actuality, it's a little more complicated than that. And you all probably can relate to some of these factors and might even bring a smile to your face, because the first factor, this T sub n, is the time from fire to annunciation. And if I could ask you what that means, hopefully you would say that a fire starts and burns, and at some point, either a person or a device, a smoke alarm, smoke detector, a heat rise sensor, detects a fire. That time between the ignition and some detection where annunciation happens, meaning an alarm, a strobe, and a horn, that time has to be considered part of this evacuation time to get a realistic view of how long it takes to egress a building. The second factor is the time from hearing the annunciation to a decision response is needed. And this is always kind of interesting, because for code people, that reaction time can be delayed. And I often talk about a code conference where we had a high-rise hotel full of code people, and around 10 o'clock that night, a fire alarm sounded. And I was at about the 5th floor, and my beautiful view out my window was the top deck of a parking garage. So I went over to the door, felt the door, opened it. No one was in the hallway, no smoke, alarm was sounding. And then I went over and looked out the window at the top deck. Thought, well, I don't think I'll leave. Now, my reaction time was 0, or my reaction time was hours, I guess you could say. The next day in the lobby, I met with some other building officials and asked if they had heard the fire alarm. They said yes. They had made their way to the lobby with about 5 other building officials, and no one left their rooms. So the reaction time was really poor for people that know better. The next factor, this T sub PA, is pre-evacuation activity time. And many of you, if you've ever been in a situation where it wasn't a planned drill where you knew it was coming, you sit and think, well, what should I take with me? Should I take my laptop? Should I take a particular set of files? What should I do? That pre-activity time often puts people at risk, because they're trying to figure out what they should gather to take with them. Not only does that slow them down in egress, it delays their initiation of egress. And then lastly is the actual time to travel to the exit discharge. So when you add all of those things up, you get a much different period of time than just the travel time. And all of those are considered when we're talking about the evacuation time and travel distance when we're talking about egressing a building in an emergency. Now, people movement is an important consideration. As we said, average walking speed is about 250 feet per minute. Shuffling speed, less than 145 feet per minute. And that might be somebody that's older, that might be using a cane. And the average flow rate is about 25 people per minute for feet of width. And that's why when we design egress corridors, the width becomes critical and the design occupant load become critical. And going downstairs, you'll notice 21 people per minute per width, but upward travel is less, 19 people per minute per foot of width. So that gets to be very difficult when we're trying to understand how people move, and lifting your body up steps is obviously more strenuous, takes longer than dropping your body down steps from an elevated floor. You know, it's interesting to note that flow rates can increase by half, 50%, in passageways less than 10 feet long. And as a result of that, you can understand why dead-end corridor lengths get to be critical. Because at some point, that passageway, that dead-end corridor that's longer than 20 feet, can actually increase egress travel. Now, all this, these studies that give us these numbers are incorporated into sizing our egress system. Another interesting statistic, and this is something that most people don't realize, most injuries that happen in buildings happen on stairs and happen because of trips or falls. And it could be even one riser. And falls in a public safety world are incredibly important. There's lots of studies, a lot of study research been done to understand these falls. And I thought this was curious because you'll see that Canada and Mexico, I guess more people died due to falls between these dates per million population than in the United States. But for some reason, Spain, if you look over here on the other column, they don't, not as many people die. It's curious, I don't know why, but these numbers help us understand relative to other countries' code structure, population demographics, the risk when we're dealing with changes in elevation, steps, those types of things, that low lighting levels that can cause people to fall. Now, don't live in Hungary. I don't know why, but these states are very dangerous. Now, I don't know if Norway is because it's icy, and Austria, but you'll see how the United States is actually fairly low when it comes to the number of unintentional injury deaths due to falls. As a graphic, you'll see that Europe and the Scandinavian countries, Greenland and Iceland, have a mortality rate higher than the Soviet Union, the old Soviet Union, China, and the United States. And it may be climatological, but Europe kind of throws a wrench in that. And then population densities are low in Africa, but they're very high in India, yet the mortality rates for falls are very different. So this type of information is fundamental to understanding how the code can address those egress and walking surface issues that deal with lighting, changes of levels, uniformity of egress stairs, that type of thing that gets built into the code. Now, if you look at what happens with age, and this is more and more obvious to me as I get older, but you'll notice that the World Health Organization has broken down the world into 6 zones or regions, and it looks at the differences by age and by male and female, the mortality rates from falls. Now, if you notice, all ages, generally, guys die from falls more than women, and that's just the way it is in almost, I think, every case. Not quite 2 to 1, but sometimes more than 2 to 1. You notice in the Americas, it's more on parity, but many of these countries, it's more than 2 to 1. And you also notice that when we deal with age, as we age, it's very clear that in the world, especially at this more than 80, things tend to switch. Women tend to die from fall-related injuries. Now, it may be that there are just less men around at that time and the higher population of women, but you'll see that up until that age bracket, men generally at least 2 to 1 and maybe more. Understanding these fall-related statistics, again, play into our lighting, the uniformity of riser and treads, the slipperiness of walking surfaces, egress lighting, those types of things. Now, when we look at falls and we start to apply this to buildings, we look at stairs and steps, ladders, or stumbling, and next to that, other falls from one level to another. Now we get to see, relative to the type of falls, where people fall the most, and these numbers have been increasing steadily. And you'll see that the stairs or steps, the third column on the left, 1389 and 1998, and falls from one level to another, 1187, dominate where we would find people falling. So we want to make sure that stairs and steps are safe, the treads and risers heights are uniform, they're secure, the handrails and guards are secure, and those surfaces are well lit. Now, lest you think that we've done a good job of this, you'll notice the 1990 number and the 1985 number match on that other chart, but this is what's happened since then, up through 2018. And you'll see the number of deaths due to falls in the United States is just continuing to climb. Now, our population is aging. We try to do a better job with our buildings, but we have had a steady growth in the number of deaths falls. Now, that means that we've got to do a good job or a better job when it comes to those parts of these falls that are in buildings. And this does not break out those like the previous chart, but you'll see that the number of falls has from its low in 1985, 12,000, to 37,000 in 2018. Now, our population has grown, and if this was normalized for population, I think there would still be an increase. It's about a 312% increase between the low in 1985 to the 2018. And the population has only increased 36%. So a 36% increase in the population, but a 312% increase in the number of deaths due to falls is an interesting statistic. Now, this is something, when you make an evaluation of what a serious hazard is, comes into play, because if the existing building that you might be looking at doesn't have a proper illumination, treads and risers aren't the same height, or they're loose, or the handrail is loose or missing, we have some context for saying that's a very dangerous situation, because we know that there's a high risk of death from those types of falls. And in studying people movement, especially in level passageways, because generally all of our corridors, hallways, lobbies are level, this chart kind of helps us understand what happens as speed decreases. That's the left column, is 1, 2, 3, 4 miles an hour. And across the bottom is the number of people per square foot, or the number of the square feet per person, I'm sorry. So at 20 square feet per person, at 3.5 miles an hour, you can see that at 20 square feet per person, generally people are moving at about 3.5 miles an hour. As I decrease the square feet per person at 7, which would be considered, 15 would be considered tables and chairs in an assembly occupancy, If I'm egressing from there, I'm slowing down at about 3 miles an hour. At 7, where I have chairs, unsecured loose chairs, I'm down to about 2.25 miles an hour. And down at 5, where we have standing room only, you can see you're into the shuffling range and you're only moving at 1.5 miles an hour. And as I decrease the square feet per person, eventually, as I approach 2, which looks a lot like what might be the case 2 or 3 in that nightclub fire, you can see that I'm barely moving at all, or I've stopped. And once they started pushing to the exit, they were less than 2 square feet per person. Generally, that's a jam. That's where people are not moving. Then they start pushing and climbing over each other, and that's what happened at the doorways to that nightclub fire. So these pieces of information help us evaluate the risks in buildings when we understand. And there's a second chart I wanted to show you. This is from a 2015 study of a heterogeneous population, meaning they had people of different capabilities, different walking speeds, and you'll see again miles per hour of people per square feet at the top, feet per second to the right, and you can see that same curve. As the density goes up, the ability of people to move drops dramatically and can lead to death in the event of an emergency. Now, there are some assumptions when we're dealing with evacuations from a fire that are built into the code. There are methods to save people or to bring them to safety, and you always have to consider the combustibles and the commodities and how they burn. And you'll know that research has been done, testing has been done to develop smoke development ratings and smoke spread and smoke development, because we need to know how that stuff burns and what gases get off gases when it burns and how quickly it burns. And that's all provided from testing materials that are used in buildings, because it affects the tenability of the space. Now imagine a fire starts in a room. Depending on the type of materials, it burns at a certain rate. And as it burns, it produces smoke and toxic gases. So there will be a level that begins to move down in that room as that smoke gets parked at the ceiling. And as more and more builds up, that line of tenability moves down. And at 6 feet above the finished floor, now my face is going to be in that smoke. And if it takes me long enough to get to the point of exit access, I may be overcome. And even if I begin to move down, crawling on the floor, eventually that whole space will be filled with smoke, depending on my proximity to the fire. Those pieces of information dealing with tenability get to be incredibly important. And we want to talk about some of those tests and how that data is produced. In a fire scenario, generally works like this. They'll have a room, and they'll use a commodity like oak as a baseline, and they'll put a grid of this oak material in a corner, and they'll begin to burn it, and they'll measure the rate of growth, how much smoke it produces, and that red oak becomes the baseline against which we compare other materials. We measure the heat it releases and the time it takes to make that space untenable. And because of that, we can predict with some certainty how many people can be in a space, can evacuate the travel distance that's necessary in uncomplicated circumstances. So I'm going to show you a picture of one of those tests. This is a furnace that is burning a product or a material, and you'll see that it's the ASTM E119 test. This is a protocol that lays out how and what has to be tested. You can see the sensors on the glass. You can see all the wiring that connects to the evaluation equipment. And you notice this particular fire has been going on for 1 hour, 11 minutes, and 4 seconds. So this material may have a 1 hour rating. This may be testing a wall panel. They may be testing some other material. But this furnace and this method for evaluating materials is done for almost everything done in a building. In fact, you will find wall assemblies, for instance, that will be put in a furnace, just like the one we looked at. And there will be temperature readings at the interior and exterior surfaces. And then internal to the material, there will be temperatures taken, and those will show the time temperature curve. You notice that on the inside here, it indicates that there's 1900 degree temperature measured on the fire surface. And as I move through the material, the temperature drops until the back surface is only 130 degrees. Now, it might be a little warm, but I'm protected from fire for a given 2 hour exposure if I build this wall of this material fastened in a certain way. And that rating and listing then is cataloged so that designers can use it to provide a code compliant separation from another tenant, another space, another occupancy, or another hazardous material storage. Now, the equipment we use to do that are things other than that furnace I showed you. For instance, this is a device that's the protocol for using is set up in NFPA 253, and it's a radiant flux test. It's really curious. This is kind of interesting. This test was developed over 30 years ago, and it measures radiant flux, obviously, but that means the rate of the flow of energy as radiation, heat, measured in watts. And what happens in this tray, you'll mount a material, a carpet, or some other material that will lay flat where those two handles are on that midsection of the device. And it's on the right side, it's closer to this angled heater. You see this angled device inside that chamber. The door is open. That is ignited. It's a hot surface, and what we're trying to measure is the time it takes for that material to ignite. And as the flame moves away from, or to the left in this tray, it's moving further away from the flame, and we're measuring how much energy it produces in watts, how long the material will burn, and when it will ignite, because as it moves away from that source, there's less and less radiant energy from that burner, and we're trying to measure how long it takes, how far it will burn, and if it will self-ignite as the temperature diminishes. Now, this is used for a lot of materials, and the information we gather from inside this test chamber then gets applied to those materials as a NFPA 253 compliant material, and can be used in a certain way, in a certain application, with certain rating. And all of this works together because we will rate assemblies, give them test numbers for burning in a furnace. If they comply with a standard, they'll be listed in a listing like UL or some of the other Warner-Kersey listings. It will have a label attached to it. Many of the tests that are done for most materials result in a label being affixed to a material or device. And then the construction documents reflect those code requirements and incorporate listed rated assemblies, listed and labeled materials, and in enforcement, our job then is to field verify that what was specified, what was approved, is actually being built. Without that testing, Without that listing and labeling, this would be almost an impossible process. 2 years ago, I met with some building officials from, I believe it was Pakistan, and some of these countries do not have the testing, listing, labeling, the university research that we take for granted, and it's a very difficult process then to assure that buildings are safe and sanitary without this underlying basis of research, data, statistics, and information. You'll see many of these things. For instance, U.S. Gypsum Association puts together a fire resistance design manual. When I have to separate spaces, creating a protection for adjacent spaces by putting rated assemblies in place, I may use one of the manuals like this that includes detailed information developed from testing. And you'll notice this tells you here were the fire tests that were being done, bottom, middle of the page, UL R11270 or UL Design U329. And there's even a field sound test that was done. But this assembly, if it's built this way, one layer of half-inch thick proprietary cementitious backer, 2x4 wood studs, 16 on center, 1.5 galvanized roofing nails, or 1 5/8 wafer head screws. It gives you the spacing, what type of insulation was used, the proprietary gyp that had to be used. All of this is a description of WP 3441 up there in the upper left, a 1-hour rated assembly. And that's how we assure, because it's been tested, that we can provide a 1-hour amount of time that occupants on the other side of that rated assembly can egress in safety, protecting those around the fire. Now, the other thing that we do in the building code, and you're going to hear this many times during the course of the Code Academy, is that the building code is a risk management tool. It's a risk management device that we put in place to help people deal with the risks they're creating by the way they want to build a building, what they make it of, how big it is, and how they're going to use it. And there are several factors, several elements of risk that we can discuss. And I think most people, the public, non-technical people, would understand, would make a building riskier or less risky. Things such as, and if I asked you to tell me what those were, without using code words, without using the jargon we use every day, I would suggest that these are some of the important elements of risk. Understanding how people move, how quickly they move, what speeds they use. We can then say these factors need to be addressed. Things like, oops, sorry about that. Things like whether occupants are sleeping or not. If we have sleeping occupancies like the institutional assembly occupancies like hospitals, or the residential occupancies like R1s, 2s, 3s, etc. When occupants in a building are high risk, and we have to address that risk by doing things like incorporating smoke alarms, suppression systems, horns and strobes that basically replace a person and the person's senses. Because when you're asleep, you're almost paralyzed, it would be as though you were hiring somebody to stay awake and listen, hear, feel, and yell if there was an emergency. We do that with devices like smoke alarms, smoke detectors, annunciation devices that yell, smell, and see if there's an emergency. So we build those things in because sleeping occupancies are high risk. Another risk factor is familiarity with surroundings. In your home, you're much more comfortable if there was an emergency than if you were in a business somewhere, in an office building somewhere that was not a place you're familiar with. So familiarity helps reduce the risk, and how familiar our people are with their surroundings becomes important to understand. Travel distances and multiple floors to safety, we've already talked about. Traveling up or downstairs, how people move with non-homogeneous populations, that we have to design width, quarter width stairways, rated stairway enclosures, rated corridors. Those types of things are based on some of that information we know, but as travel distance and floors increase, risk increases, as well as the capability of occupants to respond in an emergency. That's why a hospital has a high level of risk and has incorporated into the building features far beyond what might be in an office building, because occupants will be sleeping, not familiar with their surroundings. Hospitals can be very large, and an occupant may not be capable of responding at all. So we may have to change our strategy and protect in place because they may be sedated, they may be post-surgery, or unable to walk at all. Higher risks when capability to respond decreases. The same thing with willingness to leave. That's unfortunately an issue in dwelling units. As I explained in the hotel, sometimes people aren't willing to be inconvenienced and put their lives at risk. Understanding those factors for egress time, it can be really important, as well as the number of occupants in a space. And obviously, everybody understands the bigger the crowd, the more risk is evident when we're looking at how we're going to design a space, the number of occupants in the space. Sensory impairments or limitations. Now, in that nightclub, you would have several of these factors because as people drink, their senses can be impaired. Their willingness to leave might decrease. Higher number of occupants in a space, their capability of responding then, as their sensory impairments increase, decreases, and their familiarity with surroundings might not be what it should be. All of those things, sensory impairment can be even the noise from music and talking that may make hearing enunciation of a fire more difficult, thus the risks go up. So nightclubs will have some of the highest code requirement of many occupancies. And then the likelihood of panic in an emergency. It might be if you're in a movie theater with your young children, there might be a high level of panic if there was an emergency. Obviously, when it's dark in a movie theater, your sensory impairment increases. There's a high number of occupants in the space. The travel distances might be unclear, and people are not familiar with their surroundings. So you can see those high-risk occupancies incorporate many more building features to address those risks. Exposure to potential hazards. High-hazard occupancies have some of the highest requirements for separation, suppression, detection, and alarms because there is a potential to be exposed to some really hazardous materials and products of combustion. And then specific loads, wind loads, snow loads, seismic loads, flood loads, all of those things that might climatologically impact a building produce elements of risk. Ohio tends to be a wind flood state, not so much seismic, but those factors are incorporated into a design. Now, if we don't have any questions, I'm going to keep going. Is that all right, Meg? Now, there are some risk management strategies that we talked about briefly. For instance, in a hospital, I might protect in place as opposed to evacuation. In a school building, I'm going to evacuate. We regularly hold drills so that people are familiar with their surroundings and know where and how to move. In a hospital, however, we are going to need to protect in place, which means I compartmentalize, I use ratings and listed materials to provide safe places. In high-rise buildings, I might have areas of refuge for people that can't egress in stairs if the elevators discontinue operation. And then for those places that might have hazardous materials, I'm going to address the quantities. I'm going to try to contain that quantity. I'm going to try to protect adjacent occupancies. So there are different strategies, but we're trying to make sure our building and equipment and systems, our building are at balance with the risks that are produced by how a building is used, what it's made of, and how big it is. Now, as risks increase, then we have to add features. For instance, from fire, as risk conditions are added, they must be offset, and the purpose is offsetting those risks. For instance, there may be a required amount of travel time to safety. We want to assure that as risk conditions are added. They might require additional amount of time to get to safety because I've added risk features, like increase in toxic gas production, which would reduce the time we have to reach safety. So depending on what's in that building, I've got to add features to manage that risk in that occupancy. Increasing travel distance obviously increases the time necessary to reach safety. So if I have increased risk, I have to understand that my travel times, as they increase, risk levels go up because I need longer time to reach safety. And if there are materials that are introduced, I may have to build extra building features in to deal with that additional risk. And delays in the time when occupants are warned increases the time necessary to reach safety. So all of these things I need to assure I understand as a designer, use those strategies for managing risk, and we do that in the building code through several things, like a fire protection system. I'm going to design a fire protection system for a specific commodity that's under it. Fire protection systems aren't one size fits all. Their commodities are determined, what it has to react to, depending on how much heat is produced, how fast it burns. Those factors will help me determine what type of fire protection system, the density of heads, the amount of water flow that I need to incorporate into a building. The egress system is a way I manage the risks in a building. That egress system is not often thought of as a system, but depending on my travel distances, my numbers of floors, the type of hazards I'm exposed to, the capability of the occupants, my egress system has to respond. And that's how I manage some of those additional risks, by managing and adjusting my egress system. The fire resistance and fire separation become critical in multi-story or multi-tenant spaces where an adjacent space needs to be protected from an adjacent occupancy of different fire risks. And so understanding how a building and how adjacent spaces in a building are used is necessary to develop the right separation and resistance ratings for those components of the building. Also, allowable height and area. The code restricts certain occupancies to different heights and areas depending on how a building is used and what it's made of. You can read out of the building code which occupancies are more hazardous and include more risk by just looking at the allowable height and the allowable area. You'll notice between occupancies, different amounts of allowable area and allowable height. As an occupancy is riskier, in fact, if you look at one occupancy type, but move across construction types, you'll see as the construction type becomes more combustible, the allowable height and allowable area diminishes, trying to balance the risk with the building limitations. And as I said, the more number of stories and longer travel distances to safety obviously is an increase in risk. So we're going to deal with that by making sure we balance the height, the area, how something's going to be used, and what it's made of as one of the fundamental parts of the building code. Also, we will see structural requirements that are incorporated, different structural requirements for different components. The main structural components of a building might need to be protected to a greater degree than other components, depending on how a building's used and what it's made of. You'll see construction type, a classification of different types of construction so that I can rank, classify hierarchically what a construction material can do as it performs in an event of emergency, a fire, seismic loads, wind loads, snow loads. So that construction type is a risk management tool, and as well as the pieces and parts I put into that building manage risk. The mechanical system provides fresh air, provides heat, cooling, and the larger a building gets and the taller it gets, the more important that for those occupants is the ability of that mechanical system to deliver conditioned air, or sometimes even to be used as a smoke evacuation system when it's run in reverse, basically. Or the electrical system is a way to manage risk. That electrical system in a building will power many of the components of the system that will warn me in the case of an emergency and provide lighting. And even then, the electrical system will include things like battery backed up components to make sure that all times the building's occupied, those safety systems manage the risk in a building. Now, oftentimes people don't, as I said, for example, don't consider an egress system a system. And I just wanted to show you what I mean by that. In every building, in every space, you'll have a system that helps me egress safely. That means from the point of time and space where I live in that building to my exit access, down a corridor to the exit access door that gets me into the exit, that's a protected, rated, safe haven, that gets me to the exit discharge where I leave the exit, and to the public way, the safety. That system must be designed with the many, many variations on height, area, occupancy, use of a building, construction types, and all are designed to make sure that occupants in a building can egress in a reasonable amount of time with respect to the risks that are available. And that system is critical. That's why you'll spend much time in Chapter 10 and Chapter 7 dealing with these pieces and parts of this egress system. And we could do the same thing for each one of these other systems that are used to manage risk in a building. Now, when we're determining safety, we're going to ask how is the building and its spaces, how are they being used? That's critical. And then how is the building constructed? What is it made of? And how big is the building? And those risk factors and those tools to manage the risk are the fundamental backbone of the building code to help us provide a safe and sanitary condition that meets the intent of the law, that doesn't show preference of one material over another, that provides for uniformity, and it sets performance objectives that designers can meet to assure the building safe and sanitary. And when we use the codes, there's a whole process of code development that you can see starts with the design of a building, continues through the review and approval, and once that approval is given, because we have looked at the risks, we've developed risk management strategies, and we have designed a building to comply with those risk management provisions in the code, and that information is passed on to a building department for review and approval. And the importance of that approval is that the law says that when an owner in good faith manages the risk in their building they want to build through the code provisions, the building department will give an approval that becomes a license. And that license indicates that the building owner has a legal right to build what was reviewed and approved, because the process has confirmed that that building has managed the risks that were endemic in how a building is going to be used, how it's proposed, what it's proposed to be made of, and how big it's proposed to be. And that license then is initiated in construction beginning. And once construction begins, there's a trust but verify process that begins. And the building department is to make inspections, not to approve anything any longer. The building has been approved, but make sure what gets built matches what's approved. Because when the building matches what's been approved, there's a high level of assurance that the risks have been managed and the people will be safe and sanitary in that building. And during that process, there's a whole level of testing, labeling, and listings that are confirmed. Concrete, for instance, has on-site testing, but the components of the concrete, the sand, the gravel, the Portland cement, the admixtures, all have been tested, all have been listed for combination to produce certain results. And the testing that happens in the field is to make sure all of those components have been used properly and that those materials perform properly. And once the process begins, it moves through to completion. And then we want to incorporate a mechanism for making sure that that building is maintained as approved. And that's really the fire prevention process. Now, there's some overlap during construction inspections and testing, and the building department even overlaps into maintain as approved if you would look at chapter 34. But we trade off much of that responsibility to fire service to make sure that someone is continuing to monitor, trust but verify that that building is being maintained as it was approved. Now, that long process that's developed in this country, design, review and approval, construction, inspections, testing, maintenance, all are underlaid by research, data, testing, listing, labeling, and that information is incorporated into the building codes. Now, when those systems fail, there's usually been a lack of enforcement, an over-enforcement, or a natural disaster. The natural disaster is hard to address, but we harden buildings and we deal with the loads that will be imposed as best we can, trying to balance cost with benefit. When there's over-enforcement, the Board of Building Standards or the State Fire Marshal's Office for the Fire Service will get involved, because we want to make sure that what's being done is done in a timely, fair, consistent manner. And during construction, we're assuring that all of the parties are performing to produce a safe and sanitary building. And in the future, if the building is not maintained as approved and the building department is notified, the building owner now has jeopardized the public and the building official and the fire official have the right to issue orders to ask that the building be restored to the condition it was in when it was approved, when it was inspected and tested, and when it was given a certificate of occupancy. All of that is underlain by this highly technical system that produces what for decades now has been a very, very good fire record, a very, very good record of loss, and even goes so far as to incorporate other features that are not life safety, like accessibility. The buildings have a high level of accessibility now that they didn't have back in the 60s and 70s. And the energy efficiency requirements, which are not necessarily life safety provisions, but policy decisions on how we will use energy in our buildings. Our buildings are much more efficient and effective in the amount of energy they use. The materials we use are more sustainable. In fact, many of you are going to start seeing some cross-laminated timber high-rise buildings that are fantastic buildings. It's a technology that didn't really exist till recently, that are highly sustainable. They sequester carbon, but they also are beautiful and built of wood. And the fire testing and the data that was done to bring those provisions into the building code were exceptional. And all of that was done to make sure that we can preserve a built environment that's safe and sanitary, so that in the future, these types of things don't happen. And as we do a better job, these things are less likely to happen. And people can be assured, your spouses, children, and relatives can be assured that a building is safe and sanitary to use, that the built environment is safe, and that it has been developed through requirements based on rigorous testing, rigorous research, and not arbitrary provisions that favor one material over another. But when done in concert with good, effective inspections, can produce a safe and sanitary building. Meg, are there any questions? I'm about ready to wrap up.
Steve, there are no questions.
All right. Well, if there aren't any questions, you can always email us. You can, if something pops into your mind that you wanted to ask about or wanted to get a copy of some of these slides, feel free to text Meg and we'll get that information to you. Other than that, I think we'll be done for now, right, Meg?
We are finished for now. Thank you all for attending. Debbie Oler's course on web orientation for the BBS webpage is beginning at 3:30. A reminder to go to our website to click on the link there to go to the event. Given that I sent out some bad links, and I'm sorry about all of that. Thank you all for your time and attention, and we will talk with you soon.